All right, today we're going to be learning about logarithms. Logarithms is a very big thing in Algebra 2, and I think as well on the ACT, which I think some of you were taking this spring, and some of you may have already taken it. And if you plan to retake it, well, here you go, logarithms. I think are on it. I'm pretty sure they're on it. If I remember correctly, they are. It's been a while, like 18, 19 years since I took the ACT. That was a long time ago. Anyway, logarithms. So let's just get into it, okay? So let's talk about what a logarithm is. A logarithm is the exponent to which specified base is raised to obtain a given value. So logarithms are a way of sort of communicating exponents. So we've seen exponents before, but it's hard to do math regarding exponents. When you have something like 5 to the x power, that's not the same as like x to the 5th power, right? I mean, this exponent, totally legitimate to 5, but here it could be like anything. And so being able to do the math with that variable in the exponent can be really tricky, but we've come up with logarithms as a way of sort of circumventing that. Logarithms is sort of like a back alley way of kind of working with exponents and solving problems regarding variables in the exponent. So anyway, that's a long story short as to terms of what they're used for, but it seems kind of weird. I'll give you that. But just know that secretly we're working with exponents. It's the inverse operation of raising a base to an exponent, kind of like what I just wrote with 5 to the x power. You can write an exponential equation as a logarithmic equation and vice versa, and I believe that's what we're going to do first. So let me give you an example, illustrate what this property says. So this is an exponential equation, right? And I'll make something up that's kind of like that. Let's say I don't know, something that we know, right? 7 to the 2nd power equals 49. That's an exponential equation. You have 7, you have an exponent 2, right, to the 2nd power equals 49. We know this is all true. But we can write the same exact thing, not in exponent form, but as a logarithmic equation by sort of rearranging some of the terms and putting, of course, the word log in it. So log, let's write the equivalent version of 7 squared to 49 power as a log. 7 squared equals 49 as a logarithm. So notice the base of our logarithm, it's a little number, kind of like a subscript, b. That b value comes from here. And in that case, it's 7 in our example. So the base of our logarithm is going to be 7. So it's a log with a base 7. So again, it's kind of like a little subscript, kind of down half a level. And then we have a. So log base b of a is how we would say this. A is coming from here. It's what we equal to on that exponential equation, which is 49 in this problem. So log base 7 of 49 equals x. And now x is the exponent. Remember, logarithms are focused primarily on exponents. So it makes perfect sense that our logarithm equals the exponent. And the exponent, of course, in our example was 2. So these are the same equation. One is just written in exponential form and the other written in logarithmic form. So again, it seems kind of weird. It seems kind of useless right now, but it's actually quite useful when you start doing problems with those exponents. So yeah, let's try practicing a little bit. Oh, one tip I would recommend, because it's just sort of rearranging the b, x, and the a in the different spots, and then adding, of course, the word log. So what I remember is I noticed that, okay, just reading this from left to right, the first thing that shows up here is the b, right? The b number is the first thing I'm going to see when I look from left to right. And when I write my logarithm, guess what? B is the first thing I'm going to see as well. So I always remember that, whatever I see first here, like 7, if I'm reading this left to right, that 7 is going to be the first thing I write in my logarithm, and that'll be my base. So that's in terms of positioning, I always remember that the b is the first thing positioned. That, whatever number is here will be positioned first in my logarithm as well. And then I just note that the x comes second, the a comes third. Well, those are switched in the logarithm version. So x is now third and a is now the second thing that I write. So in terms of just remembering how things are sort of flip-flopped around, that's how I do it. So when I see x and a here, like I see 7 and 49 here, I know that when I put in my logarithm, it'll be the other way around. 49 will come before I write the 2. So that's how I kind of trick myself into remembering where all these terms go. So let's practice just a few, just real quick. I'm just gonna skip ahead here. All right. So 2 to the 6th power equals 64. Now to write this as a logarithm, of course, we got to make sure we write the word logarithm. Now remember the trick that, the 2 is the first thing that shows up reading this left to right. 2 is going to be the first thing that shows up in the logarithm. So that makes 2 the base of the logarithm. Remember, it's a little subscript type of number, like half a level down. Right, and then I remember that the 6 and the 64 are going to rotate spots. So 64 will be written next, and then 6, the exponent will be written on the equal sign. So this is a log base 2 of 64 equals 6. So that's my trick to remembering these. I'm just going to go ahead and click ahead here. This one would be log with a base of 4, and then switch these. Log with a base of 4 equals 1. If you want to try these in your head real quick or write them down, I'm going to put the answers up real quick. I think I've done my explanation of it. So you're welcome to just see if you get them right. Okay. All right. Of course, this goes both ways. So if you have the log form, you can write the exponential form. Same rules apply. So we're going backwards in this case. So the exponential form, remember the first thing that I see here, reading left to right, is 10. That's going to be the base of my exponent. And then remember these things switch. So the 2 will be the second thing I write, would be the exponent, and then equals 10. Or I'm sorry, equals 100. What am I saying? Because 100's last. So this is just the exact opposite of what we were just doing. What we were just doing before was we were taking the exponent version of this equation and writing it in logarithm version, but now we're writing the logarithm version in exponent version. And of course, the same rules apply. The 10 being the first thing here will be the first thing you see here. And of course, the next two values will rotate in their spots. And of course, this makes perfect sense, right? We know that 10 to the second power equals 100. So doing this conversion from one to the other will by far be the most useful thing that you can know with logarithms. Because if let's say I give you this problem, and I say, log base 10 of 100 equals x, right? You don't know it's 2, but let's just say it equals x. And I ask you, well, what is x? What's log base 10 of 100 equal? And just looking at this, you're like, I have no idea. I don't know what log base 10 of 100 is. I don't know how to do that. But if you think about it, rewriting it into exponential form can make a lot more sense. Because you would know that in exponential form, this would be 10, right, to the x power equals 100. And when you see that, you're like, oh, it's going to be 10 to the second power, so x must be 2. So it's very useful. It's a very useful thing to be able to do. I'm just going to go ahead and click ahead here as well. If you're interested, you can just try to see if you can get these right. Of course, we already did this one earlier, so I'll go ahead and skip that one. But yeah, you're welcome to take a minute, see if you can get this, and we'll move on. All right. So a logarithm is an exponent, so the rules for exponents also apply to logarithms. Let me remind you of some of those properties that we talked about way back in the day. Probably, I think it was definitely before winter break, sometime November, December-ish, maybe. I don't even know if it was before that. But we talked about rules of exponents. So let's say we had, x to the second power times x to the fifth power, right? What did this equal? Well, it kind of confuses people because they see the multiplication, so they think, oh, I'm going to multiply. Now, that's kind of true, but it's kind of not true. You don't multiply the exponents, you're multiplying the x's, right? So you have x times x already, that's x squared, and then you're timesing it by 5 more x's, which is, this is x to the 5th. So when you take these 2 x's and these 5 x's and you multiply them all together, you actually have 7 x's, right? So the trick here was that you added the exponents. And that property is going to be seen in logarithms as well. The idea of addition and multiplication kind of go together. Also, division, this is kind of like subtracting the exponents because you have 5 on top, 2 on bottom, and they're going to cancel out, and you end up left with x to the 3rd. So division and subtraction, so to speak, kind of go together as well. There's another property which we'll talk about just a little bit more near the end of this video, but x to the 2nd to the 5th power. If you have an exponent with another exponent, dual exponents, you actually multiply these together, you get x to the 10th power. And that idea of multiplying will also come in a little bit later too. So for any base b such that b is greater than 0 and b does not equal 1, so again, here's just some properties to make note of. If you ever notice that your logarithm has the same number here and here, for example, log base 5 of 5, it's always going to equal 1 no matter what. If these numbers are the same, it can be 7 and 7, it can be 10 and 10, it can be whatever. It doesn't matter. It could be x and x. It'll say log x, x. It's always going to equal 1. And the reason for that is if you think about it in exponent form. In exponent form, this would be 5 to the 1st power equals 5. And that's going to be true with anything. If you had x and x, it'd be x to the 1st power equals x. If it was 8 and 8, it'd be 8 to the 1st power equals 8. So basically, you're saying that these are equal to each other, which must mean that the exponent on that is 1. So just something to keep in mind. Little shortcut kind of trick if you ever notice those values being the same. Now the trick is if this value here is 1. So it doesn't matter what b is. It could be log base 5 of 1. It could be log 7 of 1. It could be log x of 1. Again, doesn't matter. All of these are going to equal 0 in that case. If there's a 1 right here, it's going to equal 0. And again, if you think about an exponent form, the reason why, well, in exponent form, this would be the same as 5 to the 0 power equals 1. This would be the same as 7 to the 0 power equals 1. X to the 0 power equals 1. Basically, anything to the 0 power always equals 1, no matter what. So when you say equals 0, you're saying to the 0 power. And that's always going to equal 1. So if you ever see a 1 right here, that's going to remind you that no matter what b is, it's always equal to 0, that logarithm. Now, the common logarithm. This is a pretty big deal. Common logarithms are what your calculator will is kind of more or less designed to use. I know your standard TI-84s, but more or less your regular scientific calculators will use common logarithms. Now, your TI-84s will be able to do other logarithms too with different bases. Like you can do log base 3 of 18 if you wanted to on a TI-84 calculator, but you can't really type it in like this on a scientific calculator. So on a scientific calculator, it just gives you a log. It doesn't give you the option to put something in for the base here. It just says log. And that's because it's using what's known as a common logarithm. A common logarithm is a logarithm with a base of 10. So when you see log 5, just like this, and you don't see that little base value down, little subscript little between them, you're assuming that base value is 10. So that's why you see it's equal to log base 10 of 5. You would never write this like this. I guess some people would, but it's kind of like writing the square root like this with the 2. No one ever really writes the square root with the 2 there, so no one really writes a common logarithm with a 10 there. It's sort of just a given that we all kind of know it exists. So yeah, common logarithm. If you ever see a logarithm that doesn't have a base, okay, no base here, that means that the base is 10, okay? And that's just because these common logarithms are obviously used so commonly or frequently that it just gets annoying to write 10 all the time. So just like writing the square roots. Okay, how's about this? I'll end this video here, and then we'll do 7.4 in another video. All right, I'll see you guys there. Bye.